you remember from last year, the basics of a right triangle are that there has to be a right angle, and the two sides of the triangle that touch the right angle are called the legs. The longest side of any right triangle is the hypotenuse. If you think back to last year, you may have used squares to build right triangles and to find ways to recognize right triangles, but we're going to look just at the skill of finding missing side lengths given two of the three measurements. In our first example, we have to recognize that height is the perpendicular distance from one base to the opposing vertex. So we have to search for that little symbol that's instructing us that it's a right triangle, and then we look at the side lengths. So we have to recognize that the two shortest sides are the legs and the longest side would have to be the hypotenuse. So if we use the formula a squared plus b squared equals c squared, then we can substitute in place of those variables for the values that we know. In this case, the shortest side was identified as the variable x, so we're going to substitute x in place of a. For the middle side or the second leg, we're going to substitute 13 in place of b, and for the hypotenuse or the longest side of the right triangle, we'll substitute a 17. After that, we can use order of operations to give value to both sides of the equation. 13 squared is 169, so I'm replacing that in its standard form, and 17 squared is 289. After that, we can begin to solve the equation, and since addition is undone with subtraction, we can subtract 169 from both sides of the equation, and we'll isolate our variable x squared. Once we know that x squared equals 120, we can undo that exponent by using a radical or a square root, and we find the square root of both sides. Later in the school year, we'll learn how to keep that an exact value and to simplify what's called the radical, but for right now we're going to find the approximation of x, which if I round off to the nearest hundredth place is 10 and 95 hundredths. Another example here just has some units thrown in with it, and we identify the side length 10 as being the shortest side of the right triangle, which is a leg, and G is the second side of that right triangle, and the longest side is 26 centimeters, which has to be the hypotenuse. Our formula is a squared plus b squared equals c squared. We substitute in place of the given variables, and we recognize that 10 centimeters was that shortest side, so just out of habit I tend to substitute that in place of A. In place of B, I substituted a G, and in place of C, I substituted 26 centimeters. Some basics, you probably ended the school year last year with this, but if we have parentheses here, we need to find the square of all those, so think of order of operation and grouping. 10 squared is 100, centimeters squared is centimeters squared. G squared is G squared, we're just getting rid of that grouping symbol, and 26 squared is 676, and centimeters squared is centimeters squared. Solve that equation just like in the previous example. We're taking 100 away from both sides of the equation. And when we do that, we find that G squared is 576 centimeters squared. We undo that square with a square root, and G approximately has a value of 23 and 98 hundredths. We can also use the Pythagorean theorem to determine if the triangle is a right triangle or some other triangle. And in this case, if I just take the two shortest values, where it says could 3, 6, and 8 represent the lengths of the sides of a right triangle? If I substitute those two shortest sides, which experience has taught me has to be the sides that form the legs of the right triangle, then I can just test the values of both sides of that potential equation. So if 3 squared is 9, 6 squared is 36, and 8 squared is 64, I can combine those like terms on the left side and find that 45 does not equal 64. In our last example here, we can throw some algebra into this too. This might be a little bit of a challenge right now, but it's good to see. Same thing, we've identified those legs and we've identified the hypotenuse. We see our formula here. We're going to substitute in place of the given values. A would be substituting in place of A would be x, substituting in place of B would be 5x, and substituting in place of C would be 20. No problem with the right side, 20 squared is 400. No problem with that x squared, but be careful with what's inside of parentheses here. If we have a 5x and we square it, we saw that on that previous example that would become 25x squared. Now if we combine the like terms together on the left side, we're left with 26x squareds, and we have to do a little bit of additional work with this one. We can undo multiplication with division. That part's familiar to us. We just haven't seen it in this kind of example. And what happens is that we now know that x squared has an approximate value of 15 and 38 hundredths. If we use that square root to undo the square, we find that x has an approximate value of 3 and 9/10. These were some basic examples of the Pythagorean theorem as a good review before we get into some really cool things this school year, like the distance formula, the Pythagorean theorem.